Assalamu alaikum. Welcome back to our subject mechanics of materials. So far we have covered some basic concepts of stress and strain, and we also have covered some different types of forces and its different kinds of effects, which we call later it as stresses. Then we also studied where this subject lies in hierarchy of science tree, and later in our last lecture we studied about factor of safety and how we can select factor of safety in our design considerations or in designing any simple machine part. We have covered these basic things. For the MMT concept, we already have discussed about discussed about how this subject came from mechanics definition. Mechanics, which was the study of forces and its effects, and then we divided it as rigid body, rigid bodies, and deformable. I'm just revising it as many of the students are confused about this thing, as I have gone through some answer sheets in your session 1 exam. Just to remind, imagine a rigid body. If there is a rigid body and we apply any kind of force on it, then this force either try to move it, or either will move this body from this position 1 to other position 2. The whole body will be shifted from one position to another position. But if imagine if the body is deformable and we apply a force on it, on this deformable body, then what will happen? The body will collapse. The body will collapse. The final shape can be like this. It can thin out from center, and it can increase its other lateral dimensions. So we can say in rigid body mechanics or mechanics of rigid body, we study forces and its effects, displacements, velocity, and acceleration. In all the mechanics of rigid body mechanics, we study forces and its effects, displacement, velocity, acceleration. Further, we have divided rigid body mechanics into two branches, statics and dynamics. You are going through that subject, I guess so, in engineering dynamics. And for the deformable body mechanics, we study forces and its effects. First effect is deformations, and we relate deformation with word strain, and the other effect is internal stress. So in our deformable body mechanics or mechanics of material, it is these two effects are within the material. That is why we call deformable body mechanics as mechanics of materials. So so you should remember why this deformable body mechanics or mechanics of material subject is different from rigid body mechanics. Now, further, in one of my lecture, I have gone through a difference between movement and torque. If we open or close the door, then the turning effect is called torque. But if for example there is some restriction, or there is some heavy resistance in hinges of the door, and door is not going to be open, or the door is jammed in some certain position, and it is not going to be closed or open from its stagnant position, then what will happen? We will apply some force on it, and where and door is still not going to be open or closed, then where that force is going, or the question is where that force is being balanced. So as we are applying force to open the door or to close the door, but the applied force is being balanced somewhere else. Actually, the applied force or the force we are applying to open or close it is being balanced by the resistance or the rust in the hinges. That resistance is almost same in effect, which is being which we are applying on the door edge. For example, let's suppose this is the hinge and this is the door, and we are applying force here. But let's suppose this hinge is fixed or jammed, it is not going to be open. Then this force multiplied by this distance r, what force multiplied by this distance r, this overall effect is being balanced by the internal resistance of this hinge. So we can say so we can relate this resistance as movement. Movement is being produced. Some this applied force is trying to rotate the door counterclockwise, while the resistance of this fixed or jammed hinge is trying to rotate clockwise. This internal movement or this internal resistance is basically called this internal resistance is basically called the movement effect. Okay, so we can relate this internal resistance as movement, and it is very different from the torque, as torque was the apparent property and it was the turning effect. For example, there is a hinge and it was a door, and we apply force, and after applying force, this door is at this position, goes to this position, it is being rotated. So this turning effect will be related as torque, and if there is fixity in joint, then movement will be produced, which will balance out the external applied load. So you should remember in torque there is movement, apparently movement, and movement, MOVE, movement. There is motion, turning effect in torque, and in movement there is rigidity, there is fixity, and there is restriction. Okay, there is no movement or almost zero movement. uh, uh, this was the main difference in torque and movement. So this was the main difference between torque and moment. Now we can add towards some kinds of supports and its reactions. There are many kinds of supports, but we are going to discuss only so far we are going to discuss only three kinds of supports, and we will study if we apply force on that supports, how they will react, or how they will in what direction they will show the reaction forces. Fixed support, second one is pinned support, third one is roller support. We are going to discuss only these three supports later in our bending moment chapter. We will discuss in details some more kinds of supports, inshallah, in detail. So let me show you some example of fixed support, how it look like. This fixed support, and you have shown there are many structures which are fixed in all directions. This is fixed support, and if you are going to see pinned support, it is a something pin like. For example, it is the main rod of any crane or any loading member. It is pinned here, and this arm can rotate about this pin. It is a pin support, so it cannot move vertically or it cannot move horizontally, but this link can rotate about this pin. So this was the pin support, and the third one is roller support. I Let me show you in the roller support in another diagram. So check it out. There is a roller on this bridge like structure. For example, it is the edge of a bridge, and a roller is placed at the side of this bridge. Basically, when you made structures of steel or concrete or anything, or of any material, then in winters material contracts and in summer materials expands. So thermal expansions of materials is always there with the change of weather. So to allow the so to allow the materials to expand in winter, sorry, in summer, and to allow the materials to contract in winter, you have to put a support roller like. Otherwise if we fix the supports of steel bridge edges, then it will surely break down the fixed supports. The same thing you have seen in railway bridges. The same thing you have seen in the railway bridges. There is a gap between the two tracks, the two lines. You are seeing in this close picture here, almost 1 to 2 inches, I guess so. Whatever, depends upon the coefficient of thermal expansion and coefficient of thermal contraction. Uh, well, it is the provision which is designed how much the material will expand in summer season. So if we don't put this gap, then in summer obviously the lines will press each other and the lines will deform like this. So the roller support basically is designed to allow the material to contract or to expand whenever it is needed. This bridge edge is also placed on some rollers. You are seeing here one, two, three rollers are placed at the bottom of this edge, and now the material can expand or contract on this track depending upon the thermal expansion coefficient. Uh, and fixed support is shown like this. If there is a fixed support beam, for example, then we can show it like this. And for the roller support, we can show like this. So these are rollers placed at the bottom of this beam. This is roller support, and for the paint support, we can place only here a pin like joint. Now the main question arises, basically, how much degree of freedoms these supports allow. To understand the degree of freedoms for these supports, we should first study about fixity codes of these supports. What is fixity codes? Then fixity codes mean in how much degree of freedoms these supports allow movement of the body. For example, there is a body. Let me draw a body. If there is a body, and let me draw an axis For example, it is x-axis and it is y-axis and it is, for example, let me, this one, and this is z-axis. For example, this is z-axis. Now we can say, if for the fixity code we write 6 digits, 1 2 3 4 5 6, and for writing complete code we use two words f and r. F for fixed and R for released. R mean released mean body is free to rotate up about that axis. For example, there are three coordinates, and if we apply a force and body can travel about x-axis. Okay, before discussing this, let me tell you how much total movements are there. As you are already have known about total number of degree of freedoms. First one is x-axis translational about along y-axis. It is also translational about along z-axis. It is also translational. If the motion is about x-axis, rotational. About y-axis, it is also rotational. About z-axis, it is also rotational. So these 6 degree of freedoms we can have. That is why the fixity codes have 6 digits. Now we try to check. For example, if the body is for example, if the body can move along x-axis, then we can write as x translational is permissible, or we can use the release word. Along x-axis, the body is free to move along x-axis and body is released. Okay, so if the body is also free to move along y-axis, then we also use the word released r. And for example, if body cannot move about z-axis, it is fixed along for the z-axis, then we can use word fix f here. Okay, so now we should check for the rotations. If the body can rotate about x-axis, rotation about x-axis can rotate, then we can write it as body is released. And if body can rotate about y-axis, then it is also released. And for example, if body cannot move in about z-axis, then we can write it as it is fixed in rotation about z-axis. So these 6-digit code are completed. Now we can use this study on our 3 kinds of support. For example, For example, for the first kind of support, fixed support, we write 6 lines, 2, 3, 4, 5, 6. Okay. If the body is for example, it is fixed support, and tell me, is body is permissible to travel along the x-axis? No, it is fixed. It cannot move in x-axis, or it cannot move in y-axis, and it cannot move about z not about, it cannot move along any axis x y z. So we can write it is fixed for x-axis, it is fixed for y-axis, and it is fixed for z-axis. So can this body be move about x-axis? No, it is totally purely fixed. It cannot move about y-axis. It is purely move. This beam cannot rotate about z-axis also. So it is totally fixed support, and we can write its fixity code as 6 times F. So this is fixity code for the fixed support. Now for example, if we if we put a force about along x-axis on this beam, how the beam or this support will react? Obviously, if there is a force applied from this beam on the support, the support is not going to move anywhere. The support will surely put a reaction equal in magnitude, opposite in direction. Obviously it will balance out. So we can say the body will resist, or body will react in reaction in x-axis, and body will also react in y direction, and body will also react in z direction. So for the all three translational forces, if we apply force here, this is applied force. If we apply force, then the body will react it in the same direction. And if we apply force vertically, or in around y-axis, this support will also react in opposite direction with same magnitude. That is why we write this support will react in y direction, and if we apply force in z direction on this support, this support will also react with the same magnitude. So this was for the translatory applied forces. What will happen if we try to rotate any body which is fixed from one end about x-axis? So if we try to rotate the fixed body about x-axis, body is not going to be rotate, the body will surely react. And we already have discussed that here in torque and moment, that if body is not going to be turned, or body is not going to be moved, or there is no torque, if if there is something fixed, or or if there is very heavy resistance, that the body is not going to be turned, or body is not going to be rotate, then there will be a movement generated. Okay, that movement will be surely equal to force time perpendicular distance. Obviously, But if there is a heavy resistance and body is not going to be rotate, then there surely be a movement. Okay, so write we can summarize here if if we try to rotate this fixed support body about x-axis, then body is not going to be rotate, but body will show a heavy reaction in the form of movement about x-axis. Okay, so if it is a body, and we and this is x-axis, for example it is x-axis, and let's suppose we are going we are trying to rotate it clockwise, but body will react in anti-clockwise. Body is not going to be moved, body will balance out the applied force. That balance out thing will be called as movement about x-axis. Okay, in the similar fashion, in the very similar fashion, there as in the very similar fashion as this body is completely fixed from all for all the rotations in this body is not going to be rotate about x-axis, this body is not going to be rotate about y-axis, and this body is not going to be rotate about z-axis. That is why the body will show movement about x-axis, movement about y-axis, and movement about z-axis. Okay, okay, so for the next type of support, that was pinned support, as I already have shown you here. This was the pinned support. As you are seeing, the tell me, for example, if there is a pin support, if there is a pin support like this. Okay, just tell me from here, is this body boom can travel in this x direction? No, this body cannot translate from this position to this position, or this position to this position. It cannot travel. Okay, now can this body or this link, can this move in vertical direction? No, it cannot go up or down. This support is not going to allow this body to go up and down, or to go right left, or to move even in z directions. So we can say all the translatory motions are constrained in pinned support. All the translatory motions are constrained, are fixed in this pinned support. So we can write fixity code as, for the pin support, 1 2 3 4 5 6. So all the translation motions are fixed, fixed, and fixed. Okay, so uh, for example now tell this is x-axis and vertical is y-axis. Can this body move about x-axis? No, it is not going to be move about x-axis. It is not, so it is also fixed about x-axis. So we should write it is fixed about x-axis. So for the vertical y-axis, is this body allowed to rotate about y-axis? No, it is not allowed to rotate about y-axis. It is also fixed. So this is this is in the direction of pin. This is z axis. The third z axis. Can this body, this big link, structure link, is this structure link be able to rotate about pin this z axis? Yes, this arm or this structure uh, can rotate from this position to this position about this pin axis, which is z axis. Yes, this can rotate about z axis. So for the z axis rotation, we can, it is released. Okay, for the only it has only 1 degree of freedom. A movement about z axis. Okay, so here they have summarized the wrong thing. Only in the z direction it is permissible to rotate about the pin axis of the z axis. This thing they have written in the wrong fashion. So uh, okay, now for the pin support, we should summarize how the pin support will react from this fixity codes. So for the as this pin support don't allow movement in any direction. For example, this, let me, okay, it is wound up. So this support don't allow to travel this body in x direction. So we can say that if there is a force on this pin in x axis, then this support will surely react in x axis. So we can say that there there will surely be a reaction in x-axis. And similarly, if we apply any force, or if there be any vertical force on this pin, then the pin will surely react, and there will be reaction in y direction. And similarly, this body also cannot travel along z axis. Okay, it cannot translate from in the z direction. So this pin will also resist traveling in z direction, so it will resist. So we can write rz will also be there. So, is this body permissible to rotate about x-axis? No. If it is not permissible to rotate about x-axis, then surely there will be a resistance in rotation about x-axis. So we can say the that resistance in rotation will be called as movement about x-axis. Okay, is this pin allow the motion in motion about y-axis? No, this pin don't allow the motion in y-axis, so there will be a resistance. So movement about y-axis, that will also be generated. Okay, now this is the in the direction of pin, there is a z-axis. As the body is permissible to rotate about z-axis clockwise or anti-clockwise, so we can say if there is a force which will try to rotate this body about z-axis, will there be any resistance? No, there will no be any resistance about the movement about z-axis. So we can say movement about z, it will be equal to 0. There will be no movement about z-axis. So this is the property of pin support, that in the direction of pin, the movement about that axis, that will be zero. It is the characteristics of pin support. And for the roller support, and for the roller support let me summarize directly from here. For the roller support, as translation is permissible in the x direction, so it is released, and this body cannot travel vertically downward or upward, so it is fixed. And it is also not permissible to go through the in the z direction. It is not permissible to translate in z direction. It is also fixed. Okay. And but it can rotate about x-axis, as there are rollers. It can rotate about y-axis, that is why it is also released. It can rotate about any axis. So all these three rotations are free. So we can say, Rx is 0, Rx will be 0, and there will be Ry reaction and Rz reaction, and all the other rotations are not constrained. They are free to rotate in any direction. That is why movement about any axis will be 0. It is also characteristics of roller supports. So we should remember what are the characteristics codes of our supports, and what are the reactions of that support. So far we have just studied about some kinds of supports and their fixity, or their degree of freedoms, and the reactions that supports allow, in order to the applied forces. So according to the applied forces, these different kinds of supports will react according to this thing we have studied. So far we have studied many prerequisites of this subject. We have gone through some kinds of supports, their reactions, and their fixity codes. Um, we studied these supports, as we are going to study a crane example in our first chapter, and there are some pin supports there. That is why I like to share with you some kinds of supports and their reactions we must have known before going through this example of this chapter. So 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 before, let me show you the our last lecture. So this was a factor of safety. We try to design a simple lever. We applied many kinds of forces, normal for the normal usage, jerks, loadings, temperature, environment, magnetic field, or fatigue, and we before this we selected an economical and more suitable material, mild steel, for this lever, for the manufacturing of this lever, and that was mild steel. And then we plotted a diagram, Chastain diagram, for that material, which is characteristics of any material, and that is fixed, and that is very easy to find out from literature available in books, or in the or in research papers. So after this stress strain diagram, we discussed many things, how we will select allowable stress, permissible design or working stress value for different kinds of applied environments. As the applied forces got worse conditions, we try to save our system by going far away from this ultimate point. It is the maximum point or highest point after which the body will surely collapse or body will break down. So as far as we go from this ultimate point, the body will surely be safest. uh, we try to keep our allowable or permissible point here, and we were very close to the yield point and we were not safe, and we use some more factor of safety. We go beyond from this point. Then after knowing that there would be a temperature, environment or magnetic field, then we make safe our lever, and we increase factor of safety to 3.5. And then we included some fatigue loading in our applied environment conditions. Then we then we went from, I guess so, to 6 factor of safety or 7 factor of safety. We try to save it as possible as we could. And after putting this value as far away from the ultimate, the body was at the safe locations from being damaged or from being failure. So we concluded that the factor of safety is basically going beyond from ultimate point, ultimate divided by allowable, that is factor of safety. So this was basically a design consideration, how we should select factor of safety depending upon our usage. So it was only a basic review that factor of safety is nothing but going far away from or making safe our working stresses or allowable or permissible stresses far away from the ultimate point towards a safe region, so the body should never fail in our usage. So after this these all the prerequisites we have gone through so far, uh, we should now, we are ready to start our problems from book. This is our first chapter. Introduction concept of stress. We have already gone through in very detail about concept of stress in start review of statics. There will be a review of statics. We will surely be cover some basic method or review of method of statics, as you have gone through in engineering statics course. Some of all movements about any point is equal to zero, and sum of all forces about any point is equal to zero if there is no movement. Okay, we will surely review the method of statics. Okay, and then we will try to solve this crane problem. Here we have seen this complex crane. We will try to simplify it, and we will surely try to resolve the unknown reactions, and then we will head towards finding some internal stresses and strain. So for the time our target has completed, that we are ready to solve our book problems inshallah. For from next lecture we'll start this problem. Best of luck. We'll see or we'll meet inshallah in our next class.